Hi everyone, this is Miss Rosita. We're starting our new chapter. That's chapter 4, looking at the first section on exponential functions. And first and foremost, you need to know what an exponential function is. So you have some sort of function f of x where you have a constant b raised to a variable. As long as your variable is in the exponent, we call it an exponential function. Now we do have to kind of make sure we specify that this constant, that's the base, will need to be a positive number and that it cannot equal 1, because of course 1 raised to anything would just be 1. That would be a pretty uninteresting function. So we're really looking at some positive value of b other than 1 raised to a variable x. That's exponential. So for our first example, we're going to take a look at a function where the b value is 2. So specifically, we're looking at a b value that happens to be more than 1, because we're going to contrast that in the next example where the b value is a number less than 1. So as long as the b value, such as 2, is more than 1 raised to a variable x, we could go through our table and plot some points and see what this graph looks like. So again, if I plug in, well, they did negative 3/4, but 2 to the negative third power. A negative exponent means it's dropping it to the denominator. So that really would be 1 over 2 cubed. And 1 over 2 cubed is 1/8. And I could do the same thing with negative 2. So 2 raised to the negative 2 power would be 1 over 2 to the positive 2 power, or 1/4. And then continue on filling in your chart and plot your points. So what you can see happens with the graph is that as x gets bigger and bigger, our function goes up steeper and steeper. And as x gets smaller and with negative values, and it's going to flatten out at a height of 0. Important to kind of, I guess, think about the fact that there's no way that you could take 2 and raise it to a power and get a negative number. Even when x is really small, meaning like negative 5 or negative 10, that's just going to put 2 raised to that power in the denominator. It's not going to make it a negative number. So our graph, even though as we're approaching off to the left as x goes to negative infinity, the y-coordinate is never going to drop below the x-axis. It will always be positive. Okay, so they have some reflect questions. First one says what happens as x gets bigger, and then what happens as x gets smaller. So this is our end behavior that we talked about in the previous chapter. So as you can see, off on the right it goes up, and off on the left it's flattening out at a height of 0. So again, as x goes to infinity, f of x goes to infinity, but as x goes to minus infinity, f of x approaches 0. Definitely different from what we were looking at last chapter with polynomials. Okay, does the graph ever intersect the x-axis? I kind of mentioned this already, but the answer is no. And that's because when you take 2 and raise it to some power, you're never going to get a negative number. Even when x is really small, like a negative number, that like say 2 to the negative 20, that would just be 1 over 2 to the positive 20, and that's still a positive number. So you never get a negative. The domain would be all values of x make sense in this equation, and the range, well, we're never going to have it being negative. Okay, let's compare that now in our second example to a function that the b value is a number smaller than 1. Remember, it's still got to be 0 for us to be talking about an exponential function. So we're going to have a b value, let's say, of a half. So this time, if I plug in negative 3 for the exponent, a half to the negative third, that's negative sign would drop it to the denominator. And 1 over a half is really like 2. So I'd have 2 to the third, or 8. And I could do the same on all the others and plot my points. Hopefully you can notice pretty quickly what's happened is it's flipped over the y-axis. So it's a reflection across the y-axis. That's because we have the 1/2 really can be thought of as 2 to the minus 1 power, which replaces x with negative x and flips it over the y-axis. I'm going to go over that again in a minute, so don't panic if that didn't make sense. Okay, so first though, in the reflect questions, they're going to ask you again what happens when x goes bigger and smaller. So the end behavior off on the right is that it flattens out at 0. End behavior off on the left is that it goes up to infinity. So that's 2a on the reflect. Domain and range, well again, the domain is all values of x, and the range still never dropping below the x-axis. So it was the same as the previous example. And then what do you notice about the y-intercepts? Oh, okay. So if I go back up and look at my chart here or my picture, it's crossing the y-axis at a height of 1. If I scroll back up and look at the other one, that one's also crossing the y-axis at a height of 1. So when I'm looking at y-intercepts, they both will equal 1. Whether you take a half to the 0 power or 2 to the 0 power or anything to the 0 power, you're getting 1. And again, we're plugging in 0 for x to find a y-intercept. Okay, and then the last part, what transformation can you use to obtain this one from that one? So again, 1/2 to the x. This is the part that I said I would go back and say again. So here's your second shot. 1/2 is really like 2 to the -1 power. And if I have an exponent or a power raised to another power, we can multiply those powers. This would give me 2 to the -x. So if you're remembering back in chapter 1, when you replace x with -x, that's going to flip it across the y-axis. Okay? So instead of going to the right and up, we go to the left and up. Okay, we're going to move on. Third example, it says recognizing types of exponential functions. So whether this b value is a number between 0 and 1 or a number bigger than 1, again the b value, is going to make a difference whether the graph goes up to the right or whether it goes down to the height of 0 to the right. Okay, which one of these pictures you have. So if we say that it's going to go up to the right when b is a bigger number than 1, we call that exponential growth. And then when b is between 0 and 1, it's going to be dropping down, flattening out at a height of 0. And we call that exponential decay, meaning getting smaller as x gets bigger. So describe the end behavior. Well, this is a repeat, right? The growth function is the same as example 1. The decay function is the same as example 2. I just copied over what I had before for my exponential for my end behavior models. Okay, and explain why the point 1b is always on this graph. Well, if I plug in 1 for x, I have b to the 1, and b to the 1 is b. So if I plug in 1, I get b. For part D, it says explain why 0, 1 is always on the graph of b to the x. Well, again, if I plug in 0 for x, I have b to the 0, and anything to the 0 is 1. So when I plug in 0 for x, I get 1 for y. Okay, part E, it asks you to compare 3 to the x and 5 to the x. Well, both 3 and 5 are numbers, values of b that are bigger than 1, so both of them are going to be exponential growth functions. They both get bigger, they both go up to the right. However, because 5 is a bigger number than 3, it's going to go up even faster than the 3 to the x function. And at the bottom here, 3f. I take 1/3 and 1/5. Well, now both those b values are a number between 0 and 1. They're both going to be less than 1, therefore they're decay functions, flattening out at a height of 0 off to the right. However, since 1/5 is smaller than 1/3, it's going to flatten out faster. Last example, they want us to do a comparison between a linear function, x plus 3, a regular just power, x to the 3rd polynomial, and an exponential where the variable is in the exponent. So I complete my table, that's pretty straightforward, and then I do the graphing. So they've graphed the exponential function in black for us, and I compare that to the line. The idea is that as you move off to the right, it should be pretty obvious that the exponential function is above the linear function. It's going up faster. Even when you compare our exponential function in black to the x cubed function down below, again, the exponential goes up faster. It's higher. It's above the blue graph. So our last reflect here, how do the values of h of x compare? So again, as x goes to infinity, our exponential function, h of x, is going to increase more quickly, even though h of x might have started out less than the other function. Like if you look at this first picture here, our exponential was lower than our line, but eventually it's going to overtake the line. It's going to go above it. Okay, and I just put a little note at the bottom there that really what we're comparing is the rate of increase of the y coordinates. So how quickly the y is going up. So in other words, we're really starting to think about the slopes of our curves and which slope is bigger. Okay, that's it. Looks like I'm right on time. That was our bell. I'll see you guys soon.